Today what we're going to do is start applying the instantaneous form of the momentum principle that we derived and used last time. So remember that just by taking a limit, we ended up with yet another form of the momentum principle, which is that the rate of change of the momentum of a system at some instant is equal to the net force acting on the system at that instant. And this was useful because it allowed us to actually get a differential equation that we could solve to get an equation for the position of a mass oscillating on a spring at any time into the future, as long as there was no air resistance and it was an ideal spring. But there's some other things we can do with it, and in Chapter 5 we're going to explore two of the things we can do with it. The kind of problem that we end up doing is typically a little different. Usually what we were doing before is we said, well, we know the momentum of some object, and we know all the forces acting on it, so we add them up, multiply by a little time step, and now we can predict the momentum in the future, and then we can keep doing this to predict motion. One of the kinds of things we can do using this form of the momentum principle is kind of the opposite. It's to say, well, if we know the motion, that is, we know the way in which the momentum is changing, because it's doing it in some predictable way, then we can deduce F net. But more interestingly, usually, is that if F net is the sum of several forces due to objects in the surroundings, and we know some of them but not all of them, we take one more step in reasoning. We say, well, if we know the rate of change of momentum, we know F net. If we know F net and it's equal to the sum of these forces, and we know this one and that one but not that one, we can figure out an unknown force. And so often the kind of game we're playing is to figure out some unknown force by knowing rate of change of momentum and something about some of the forces contributing to the net force. So that's a different kind of problem solving. And there are two important domains that we're going to look at this in. One is can be straightforward, but we have to be careful case where the momentum of the system is not changing. And that has a name. It's called statics, because things aren't changing. It's static. And some of you will take an entire semester-long course in statics where you learn to apply this principle in great detail to analyze forces on bars and how much they bend and things like that. The other situation is dynamics, where the rate of change of momentum of something is not zero, and then it's moving in some interesting way, and we do something to understand the forces acting on it. So today we're going to talk mostly about this first case. Hope to get to that a little bit, and then next time we'll talk about the more interesting situations. We end up here with two places where it's necessary to be very systematic. Okay, a systematic approach to using this principle and applying it to this class of problems is very important. And the two places are the right-hand side of the equation and the left-hand side of the equation. And we just have to be more careful than we often are to be sure we've got it right. First of all, we need to be we need to actually determine the rate of change of momentum and to use a systematic approach to doing that so we don't let our initial reactions, our sort of gut level guesses sometimes get in the way of getting that right. And second, we actually need a very systematic procedure for identifying all the forces acting on a system. If we're not systematic, we make lots of mistakes. So even if you think you already know how to do problems of this kind, it's going to be a good idea if you just play the game as we describe it today. The game has some rules. They're clear rules. If you follow them systematically, you can solve all kinds of problems, as opposed to if you use some procedure you remember, in which case you can solve a problem you remember but not other problems. So so we're going to try to play the game carefully today. And the basic idea is just to be very careful about bookkeeping. So let's talk for a minute about identifying forces on an object. We've been doing this for a while, but we haven't actually listed all the steps that we need to go through very carefully. So I'm going to actually write them down, and we're going to try to follow this carefully. So the first step is choose a system. And so we've been doing that. We say the system is the sinker attached to the spring, for example. We're going to write it down because as we get more and more objects interacting, it gets easy to sort of slip and forget what thing you've chosen as the system. And if you don't stick to your choice of system, then you garble the analysis, and it doesn't work. The second is to list all forces on the system due to the surroundings. And one nice way to do it is in what's called a free body diagram. The simple thing to do is just represent the system as a little circle. You draw an arrow representing every force. But here's where we need to be careful. Here's where we need to be systematic, because it's easy either to miss forces or to include forces that are real forces but aren't really acting on the system you chose. They're acting on some other part of the surroundings. Or to get something that's not really a force at all but has some name that sounds official, like centrifugal force. Okay, so to avoid doing the bookkeeping wrong and playing this bookkeeping game wrong, we're going to take two steps in listing the forces of the system. And we actually know, we're going to build on what we know. We know there's only four kinds of fundamental forces: the gravitational force, the electric force, the strong force, and the weak force. And we can kind of classify them in a sort of grosser sense as two kinds. Forces acting at a distance. So distance forces. The one we've been working with all the time is the gravitational force. Why is this a distance force? Well, two objects interact gravitationally even if they're not actually touching each other. The marker's not actually touching the Earth, and yet it is interacting, because if I drop it, it's attracted to the Earth. So we're really only going to be caring about two kinds. There's going to be gravitational, and electric forces work the same way, right? Charged particles don't have to be touching each other to interact. So electric forces if things are charged. The other class of forces, and this isn't a fundamental classification, it's sort of a practical one, is what we've been calling in Chapter 4 contact forces. Forces due to two objects being so close that the atoms of object 1 and the atoms of object 2 get right up against each other, and those electron clouds start to interpenetrate. So contact forces. And the thing that we all trip over on this is that in order to exert a contact force on the system, an object must actually be touching the system. So touching system. And if it's not touching, then, and it's not interacting with one of these distance forces, then we can't count it in our systematic procedure. Now, it may be important, but it gets taken care of indirectly, typically, if it's important. So here's an example of something that I think there was even a problem on the test. You throw a rock. So here's a rock. You've thrown it. It's got some momentum. What are the forces acting on the rock at this instant? Well, let's apply our procedure, and then let's draw them on our diagram. So first of all, what's the system? The rock. Second, distance force. Yes, and the way we're going to identify these forces is we're going to write down the name of the object in the surroundings that's exerting the force. And that's very important, because if we can't identify an object that's exerting the force, then we should wonder if it's a real force or just something. So gravity, and what's the object that's exerting the gravitational force? The Earth. Okay, so we were going to put a gravitational force, and in parentheses we're going to put Earth to show that we picked a real, here we'll put system, we picked a real object in the surroundings. Okay, now in the real world, so the rock is presumably not electrically charged because it didn't tell us it's electrically charged, so presumably there are no distant electric interactions. So are we done with this? Okay, so there are some other gravitational interactions, the moon, Venus, whatnot. They're so much smaller than the effect of the Earth that we're justified in neglecting them in this case. But somebody said air resistance. That's right. There's air resistance. And the air resistance force, sometimes called drag, acts in a direction that's opposite to the velocity of the object at this moment. So it would be acting this way. I'm going to call it drag. And it's due to the air, which is an object in the surroundings. And what else? We done? Okay, now it's pretty common to want to say your hand, because you threw the rock. But does the hand work according to our rules of the game? It's not, well, it is interacting gravitationally at a distance. There is a gravitational interaction between my hand and the rock, but it's very small. So we'll neglect that. Is my hand at this moment touching the rock? No, I already threw it. So it's left my hand. My hand is not touching the rock. So we can't count my hand. We can't count my hand. But if the rock hadn't touched my hand, it wouldn't be flying through the air. So how have we taken account of the fact that it's sometime in the past? It's summed up into the momentum now, isn't it? It's already added up into the momentum now. So that past interaction has already been taken account of. And if we wanted to analyze that, we could go back to a time when the rock was in contact with my hand, and we could consider the impulse my hand gives it while it's touching. Then it would be touching. But at this moment, my hand's not touching it, so we can't count my hand, but it's been taken care of already. It's already in that momentum. Okay, so let's try it on a fairly straightforward situation here. And we'll practice it together. And so we've got a block hanging from a string. String's attached to the ceiling. Here's another string. Your hand's pulling on the string. Okay? So by implication, since the question is what objects exert significant forces on the red block, what have we chosen as the system? The red block. Okay, so the red block is the system. Okay? So now let's see what we have to write down as the forces acting on the red block. Okay, so the most popular answer is answer 1. And what is answer 1? Answer 1 is the earth, string 1, and string 2. So the earth comes in, forces acting at a distance. The earth is the object interacting at a distance. That's correct. String 1, that's touching the system, isn't it? So that's a contact force. String 2, touching our system, that's a contact force. So that's clear. Why not the hand? It's not touching the block. But the block wouldn't be there if the hand wasn't pulling on the string, would it? The string is touching the block. How have we kind of indirectly taken care of the fact that the hand's pulling on the string? Yeah, I think you're saying it. The string is tight, isn't it? The string isn't just hanging there limp. It's tight because we're pulling on it. The fact that the string can exert a force on the block is due to the fact that our hand is exerting a force on the string. So if we could take the string as the system and say, well, the hand is touching it, the block is touching it, they're both interacting. But since we took the block as the system, we only use string 1, string 2, ceiling, same reason, right? String 2 is hanging from the ceiling. It needs to be there. It's responsible for making this string nice and tight when we pull on the block. But it's not touching the block, so we don't include it. Okay? Questions about that? All right. So we've got all the forces. We've got a list. We've got string 1, string 2, and the earth. And so we want to, it's useful to record these things in a physics diagram because we want the directions to be recorded. So making a free body diagram helps us record the directions. So let's start our diagram. We'll do it right here. Okay. And we're going to put the names of the objects just to be. So the gravitational interact the Earth, force due to the Earth, that's a gravitational force. We certainly want to draw it down. We say F gravitational, and we put Earth to keep ourselves honest. Okay. And what's the direction of the force string 2 is exerting on the block? That way? That way. So we should draw string 2 here. We're going to call it a tension force because that's just a name for the kind of force exerted by a rope or a wire or a string or something like that you're pulling that's under tension. Could be a spring. So it's going to be a tension force. We'll call it T2, and we'll say it's due to string 2. Okay? Now there's one more piece we haven't included. So here's our incomplete force diagram. And now we need to draw the force due to string 1. So which of those arrows should we, it shows the direction close approximately that we would use to indicate on our force diagram the force due to string 1. So think about how a string works. Okay, just think about strings. Okay, how does a string work? Okay, so 3/4 of the class says 8, and then there's some 1s and 7s. So 1 is up, 7 is to the left, 8 is in between. And this is actually, it's not a trick question, and it really is along the string. So strings are limp things unless they're stretched under tension, and a string can only exert a force along the direction of the string, so that we need to draw the force due to the string in the direction the string is going, and we'll call that Ft1 due to string 1. So that completes our diagram. Okay? Now, it's true that there needs to be a force up because the block's just hanging there, right? It's not falling or anything. And it's true there needs to be a force that way because the block's sitting still. We're drawing some conclusions based on the momentum principle. And yes, that force has both of those properties, so we're going to be in good shape here. That's going to work. Okay, so we've got 3 forces acting on our block. And now we're going to apply the momentum principle. So we've chosen a system. We listed all the forces. We did those things. We drew the diagram. We wrote the names of the object. We're pretty sure we're done. So we're ready to apply the momentum principle. What is the rate of change of the momentum of this block? 0. 0. Okay. So we can write the momentum principle in the following way. We have dp dt is f net, and this is a 0 vector, and this is ft1 plus ft2 plus gravitational force, and they all add up. They should add up to 0. Now, because this is a vector equation, it's really 3 equations. It's dp x dt is f net x, and dp y dt is f net y, and dp z dt is f net z. And so it's often easier to solve these things if we write these out. So let's actually try. We want to be able to write out those equations. Well, this force is easy. Okay, this force is just 0, and it's going to be a minus mg 0. And this force, well, at least we know the direction. It's so we can write it as the magnitude of the force, which is the magnitude of the tension in direction 1, 0, 0. And we can write this as the product of the magnitude of this T2 force times some unit vector, and now we need the unit vector. Because if we get the unit vector, then we'll know the x and y. We can divide this force up into x and y components, even though we don't yet know its magnitude. Okay, even though its magnitude is currently an unknown, we still can get this unit vector if we know an angle. Okay, so let's think about that. In order to write out x and y components of this, we need the unit vector in this direction. And we're told here that this angle is 40 degrees. And often the way problems work is that you're told angles. Even though it's a little odd to run around with a protractor, you're much more likely to be running around with rulers. But in any event, we're told that this angle theta here is 40 degrees. And so we want to be able to write this unit vector in terms of the angle theta. Now remember how that works. We have the unit vector in some direction. We have cosine of theta x, cosine of theta y, cosine of theta z. And this is a nice way to do it because now we know it's always a cosine. We don't have to worry about whether we got a sine or a cosine. We just got to get the angle right. So what's the unit vector we want to calculate here? Well, so about 2/3 of the class thinks it's 3, and then there's some other stuff. So let's remember how we do this because it keeps coming up. It doesn't come up every day, but it keeps coming up. So we need to remember how to do this. So we want the let's draw it here. Here's our direction, and we'll draw x, y, z axis. And remember that what is, I heard some of you say it, what is this theta x thing? It's the angle you get when you start on the x-axis and you rotate until you're lined up with the direction you want to go, right? So that's theta sub, this here is theta sub x, that's 90 degrees, that's 40 degrees, so it looks like 90 plus 40 looks like 130, so it looks like this should be cosine of 130 degrees there. Okay? What's theta sub y? But the definition is you start on the y-axis, you rotate till you're lined up with the direction of interest. That is indeed 40 degrees. And what's theta sub z? Really? It's 0 degrees. So if I line my marker up in the plus z direction, I'd have to rotate it through an angle of 0 degrees to get with the... What is theta sub z? 90 degrees, isn't it? I have to go through a 90 degree rotation to get into the xy plane. And the cosine of 90 degrees is indeed 0, but okay, so cosine. Okay. All right, so questions about this? Okay, so let's take the next step and write some equations. Here's what we're trying to do. We want to write separate equations for the x and y components. So we have dpx dt is the x component of the net force. How do you get that? Well, we add up the x components of all three of these forces to get the x component of the net force. And this is 0, so what goes there? Okay. So complete the equation. Probably a good thing to do is write it down on your paper first and then figure out which of these things matches it. Because that's what you'd have to do if you were solving a problem, right? So look at the diagram. write down the x components of each of these forces, and then add them up. Oh, and we're using the convention here that we've run into before, that if you see something like this, it's just a shorthand for the magnitude. Okay, the fact that there's no vector symbol over it is just a shorthand way of writing the magnitude of a vector. So we just want the x component of all those forces added together. All right. So 3/4 of the class says 4. So let's see where that comes from. We take the x component of the gravitational force, that's a 0. And the x component of this ft2, that's the magnitude of f2 times the unit vector 1, 0, 0. So we have an f2 there. And then we need the x component of f1, and that's why we went to all that trouble to get this unit vector, because now we just take the magnitude and multiply it by that. So we've got f1 times cosine of 130 degrees, and now we're done, because we had the x component of every. Now, this has to add up to 0. That's a magnitude, so it's positive. So this thing better be negative, is it? Yeah, because a cosine of 130 degrees is actually a negative number. In fact, it is. Did I write it down? I didn't write it down. What is it? It's negative 0.64. Okay? So that looks good. It's going to. Now, notice that we have an equation that's got two unknowns. We don't know the tension force due to this string, and we don't know the magnitude of the tension in that string. We don't know the magnitude of the tension in that string. We often say the tension in the string, because in fact, each part of the string is exerting that force on the other part of the string. So it's throughout the. So we need another equation. Suppose we know the mass. It's a mass m. If we had another equation and two unknowns, then we could actually solve and get the tension of both of those strings, even though we're not given either of them, as long as we know the mass of the object. So let's write the other equation, which of course is the y equation. Okay, so which is it? We want dpy dt is f net y, 0 equals and again, looks like you said 4. So let's see where that comes from. The y component of the gravitational force looks like a minus mg. The y component of force 2 is 0. The y component of this looks like f1 cosine 40 degrees. And now note that assuming that we know the mass of the object, we actually have enough information to solve for both of the forces exerted by both of those strings. So that's actually interesting. Let's actually do this. Let's solve for the force exerted by string 1. And let's give a mass. The mass is going to be. So we're going to solve for this tension force. And we're going to say the mass of the block is 70 kilograms. So it looks like actually we just can solve this equation, right? So we have 0 is minus 70 kilograms times 9.8 newtons per kilogram plus this F1 times the cosine of 40 degrees, which is, what's the cosine of 40 degrees? 0.768, is that what you said? 766. And this comes out to nearly 700, 600 and something or other, 86. And so if we solve for F1, it's 686 newtons divided by 0.766, and that comes out to some number or other, 896 newtons, 895 newtons. Okay, so boring, except not entirely boring, because remember Tarzan hanging from the vine? And we said, remember what happened to him? He hung from the vine and it was just fine, but then he swung from it and it broke. Well, notice this is an interesting number about the tension in this string. If the block was actually just hanging from the string, we'd have a gravitational force of 686 newtons, and so the tension in the string would have to be 686 newtons. But look what happens when we just pull it over. The tension in the string actually got bigger. Now the string has to exert a force of 895 newtons. So down at the microscopic level, what changed in the string? We zoom down in and we look inside the string. Maybe think about it as a wire. That's simpler maybe. Interatomic bonds are stretched more, aren't they? Yeah, they're stretched a lot more in this configuration than they are here. Think you could ever stretch them too much? Yeah. Yeah, so it looks like the string isn't always exerting the same force. Depending on what's happening, we pull it at an angle, it's exerting a much bigger force. The interatomic bonds are stretched more. And just maybe, what if the fact that Tarzan is actually swinging makes a difference too? Because now the string, the vine, doesn't just have to hold him there. It actually has to change his momentum. And so maybe that's going to make a difference too, and maybe that's going to mean that the vine has to even exert a bigger force. Let's talk about one other situation briefly. There's several worked out examples in the book, and I suggest that you look at them. In principle, you now know enough to solve any problem of this kind, as long as you're actually really careful to follow this procedure. There is one situation that you might not have thought of as being a static situation, though. So here's a situation. Here's a box. It's a heavy box. And you're pushing it along a wooden floor. And it's traveling at constant speed, not very fast. So it's traveling at some speed v, half a meter per second. Okay. What's the rate of change of momentum of the box? All right. So it's actually still 0. So we're still in this static situation of dp dt equals 0. And so therefore, all this stuff we just did still works. Now, there aren't any stretched strings, so there aren't any tension forces. There's definitely friction. There's a friction force, gravitational force. Okay, let's try to draw the force diagram here. So here's what the system is going to be, the box. And so here's the system. Okay, so gravitational force, somebody said, and we're going to write Earth. And so what else? Yeah. So one person said normal force, another person said friction force. Those are both forces exerted by the table, right? So the table's exerting one force on the block, not two, but it's very useful to divide it, to think of it as the sum of two different forces. So the table's got to be, since the Earth is pulling down, the table is surely pushing up. We've compressed bonds. So this is a compression force, and we do call it a normal force. So we've compressed bonds. And also, as the block's sliding this way, the table's pushing back this way because the block is actually catching on some blocks going this way. It's catching on some of those interatomic bonds, and then all of a sudden they break. And so anyway, yes. So there's a friction force. So really the table itself is exerting a force kind of like that. But in fact, since we want to resolve the forces into x and y components anyway, it's often useful to call it a normal force to the table and a friction force also due to the table. And then there's one more force, and that's the force you're exerting. And it looks like you're pushing down and to the left, actually. So it looks like the force by you is going to be going something like is going that way. And now we've actually done most of the work we would need to, and so we got the forces acting at a distance. We got the contact forces. We've got, sorry, the floor, not the table. It's the floor and you. Do we care about air here? There surely is air resistance. Why don't we care about it? It's going too slowly, that's right. So it looks like we're done. We would need to get x and y components of this force, and so someone would need to give us some angle. If they gave us that angle was 35 degrees or something, we could go through the unit vector thing and get that again. And so despite the fact that it's moving, it's basically the same thing. Just a matter of being systematic and identifying the forces, and then solving isn't really a big deal. So that's the quick overview of statics. It can get more interesting if you worry about things that we're not going to worry about in this introductory course, like the following. Suppose you have a table and you put one of those aluminum tracks on it, and then you put a cart here. Well, how much is it going to bend? And this has some mass too. If it's a massive track, then in fact the Earth is pulling down here and here and here and here. So how do you deal with that? So there's some more advanced things you can do, but the basic, they all start with dp/dt equals f net and dp/dt equals 0, and we go on from there. So you've got some homework problems that ask you to practice some of these things. And in the book, there's some problems that are a little more complicated. There's a thing hanging from two different strings, and so you have to get two unit vectors, but it's basically the same stuff.